Welcome to Point channel. Okay, today I will discuss about JVM architecture. So let's assume you have one test.java file, simple hello world Java program. Okay, so when we compile that test.java file, basically we will get a test.class file, right? So test.class file consists of a bytecode in terms of zeros and one, right? So then when we are trying to run that particular Java program test, right? How you will run Java space test, right? So exactly at that point of time, okay, it will it will try to load that particular test.class file into the JVM. So at this instance, so uh, JVM architecture will come into picture. Okay, so here, so here if you see, it has mainly three components: class loader subsystem. This is the second one is runtime data area, and the third one is the execution engine, right? So we will discuss one by one. So now let's discuss the first component is that is class loader subsystem. So as I said just sometime before, so whenever we are trying to run that Java application, that is a what you say, test dot Java, whatever, right? So then whenever you try to execute that command Java space test, right? Immediately it will try to launch one JVM instance. So JVM instance means, so basically JVM is a specification, right? So now JRE is a implementation of JVM, right? So as everybody knows, Java is a write once, run anywhere strategy, right? So once you have a dot class file, you can run that dot class file like in any machine in the sense. I mean, so for example, you have three machines. Machine one has Linux operating system, okay, and it has its own JVM, okay, and similarly Mac operating system, and similarly Windows is having its own JVM. So you can run the same dot class file in any machine, right? So so JVM is a platform what do you say, dependent. Okay, JVM is a platform dependent, whereas Java is a platform independent, right? So now whatever your dot class file, okay, so as soon as you run that Java space test, okay, immediately it will try to lift that particular test dot class file, okay, into uh, so this first component class loader subsystem, it will try to lift your test.class file into the second component, that is a runtime data area. So it will try to lift the dot class file and it will try to load class data into the method area, right? So now we will deep dive what happens. Okay, so so this is the main activity of class loader subsystem. Basically it will lift that test.class file, okay, and it will try to what you say, it will try to store that dot class file related information within the runtime data area, right? So now if we deep dive, basically class loader subsystem has internally again three what you say, three phases, we can call it as. So loading, linking, initialization. So loading in the sense, so as I said just now, like it will try to load or lift that test.class file, right? So now within the test.class file, okay, of course you might have written a main method, you might have written some system.out.println, you might have taken some help from array list or hash map or whatever, right? So then internally, okay, so like you have taken the help of some predefined classes from java.lang package such as ArrayList or HashMap or whatever. So all those classes will be loaded with the help of this bootstrap class loader. So they are loaded from jre slash lib slash rt.jar. Okay, within the rt.jar you have n number of what do you say, predefined classes from java.lang. So it will try to load all those classes from rt.jar with the help of this bootstrap class loader, right? So the second one is extension class loader. Extension class loader in the sense, okay, so sometimes I mean you want to connect to your database, either it could be a MySQL database or Oracle database, then definitely you will need respective database drivers, right? So So those drivers usually, those drivers related jars will be available in the jre/lib/ext folder. Okay. So then it will try to load those specific third-party jars from jre/lib/ext uh, to it will try to lift those jar files with the help of this extension class loader. Okay, so it will lift and it will try to keep here in the second component. Okay, so that's the job of extension class loader or whatever class loader. So the third one is application class loader. Application class loader, in the sense, it will try to lift the dot class files of your application. As mentioned in your class path. Okay, so these are the three important class loaders: Bootstrap class loader, extension class loader, application class loader. And here, what you say, the flow also, you see, it derives from top to bottom. So for example, if Bootstrap class loader is unable to find the required jar, then extension class loader will come into picture. If it is also unable to load, then application class loader will come into picture, something like that, right? So the next phase is linking phase. So linking phase, in the sense, um, so within the linking phase, we have three more sub phases, that is verify, prepare, and resolve. So verify, in the sense, okay, so internally it will cross verify the dot class file whether it is properly formed or whether it is properly compiled with the standard compiler or not. Okay, if not, it will throw the verify error or verification error. Okay, something like that. So next, prepare phase. So prepare phase, in the sense, okay, so let's assume your program has some static variables, right? So now here in this prepare phase, it will try to assign those static variables with some default values. Okay, so now, for example, integers, in the sense, default value is 0. If it's a boolean variable, the default value is to false or something like that, right? So it will assign with some default values for your static variables in the prepare phase, right? Now the third subphase is resolve phase. So resolve phase, in the sense, okay, so let's assume you are having one class A. So internally, you're also referring some class B. Okay, so now in the resolve phase, okay, it will it will try to resolve your symbolic references with the original references, right? So what does it mean? So for example, within your class A, you're having bb is equal to new b. Okay, it will what you say, that b reference variable, now it will just starts pointing to the original memory address of your b object. So that's the meaning of resolving. Okay, so now the third phase is initialization phase. So initialization phase, in the sense, okay, here, uh, whatever your static variables, so in the prepare phase, just now we discussed, it was assigned to some default values, right? So now the same static variables will be assigned to the actual values in the initialization phase. And this is activity number one. And activity number two is, so it tries to execute the static blocks also. Okay, if any static blocks from top to bottom. Okay, if you have some hierarchy, like super classes from parent class to subclass or something like that. So this is the high level description of class loader subsystem. Okay, so so I want to add two more points. Okay, so let's assume, what you say, if you are trying to load a particular dot class file, whereas the help of class dot word name. Okay, so now the dot class file is missing or it's not available. So then, class not found exception will be thrown. Okay, the famous exception. And the second one is, for example, you are having some class here in which you are also referring B. Okay. Now, dot class file for A is loaded. Now, when it is trying to look for dot class file for the B, okay. So, if in case B dot class file for B dot class is missing, okay, then it will throw no class def found error. Okay. So these are the two very famous errors. Okay. So I just want to highlight those two scenarios over here. So okay, so So the next component here is runtime data area, or which is also known as memory area. Okay, so once this class loader subsystem lifts those dot class files, and it will try to store, or it will try to keep it in the runtime data area. Okay, so then what happens? Okay, so basically it has internally again five subcomponents. Here method area, heap area, stack area, and PC registers, and native method stack. Okay, so we will discuss one by one. So what is method area? Method area in the sense, okay, method area and heap area, these two areas are created per JVM instance. Okay, per JVM instance. Okay, now this stack area and PC registers and native method stacks are created per thread. Okay, so and all these three, stack area, PC registers, and native method stack, are completely thread safe, and whereas method area and heap area are not thread safe. Why? Because these are the shared resources, right? So now we will see what is method area. So method area basically consists of class metadata. So class metadata in the sense, so it consists of information about your class, like such as your class name, method names, okay, and what you say, static variables, static blocks, okay, even in your what you say, your parent class name, your constructors. So all the information which is related to your class, so that will be what you say, stored in this method area. Okay. So this method area is also known as permgen. Okay, until Java 6. Okay. So yeah. So this is method area. Okay. So now coming to heap area. Heap area in the sense, okay, heap area consists of what you say, all objects. So whenever you create a Java object with a new operator, so basically one I mean that respective object will be created within this heap area, right? So so for example, let's assume you have a test class. Okay, so there test t1 is equal to new test. Okay, for example, if you create that, test object will be created in the heap area, right? So now uh, so now if you see this stack area, so stack area in the sense, okay, let's assume you are having some test.java inside that main method is there, right? So now you are having some big task. Okay, now you want to execute your big task with the help of three threads. Okay, now you have initiated three threads, and you have sent some task for all these three threads, right? So now thread 1 is supposed to execute some three methods, and thread 2 will execute two methods, and thread 3 will execute some four methods, or something like that, right? So then whenever thread 1 tries to execute method m1, okay, then immediately, so here you can see the thread 1 is having its own stack frames. Okay, so for m1, so within the m1, let's assume you're having some method parameters. Internally you're having some local variables. Okay, internally you have created one object like test t1 is equal to new test. Then the t1 is a reference variable, right? So that reference variable will be what you say, will be available within this your stack frame, and the actual object is available within the heap area. So now here, from here, t1 will refer to the method which is available in the heap area, right? So then within the m1, let's assume you are invoking m2 method. Okay, now in the thread 1, okay, so let's assume first stack frame 1, on top of stack frame 1, one more second stack frame will be formed to represent the m2 related method data. Okay, so if m2 invokes m3, so one more stack frame will be formed on top of what you say, second stack frame, right? So similarly, so now stack frame 1 represents M1 data, and stack frame 2 represents the M2 data. Okay, M2 method data, internal local variables or method parameters or whatever. And similarly, stack frame 3 represents method 3 data. Okay, so now once the flow executes method 3, and it will come back to the method 2, right? So then what you say, the top stack frame which represents the M3 will be will be removed. Okay. And similarly, once the flow finishes within the method 2, and once the flow comes back to the M1, then the second stack frame will also be removed. I mean, whenever you try to debug your Java programs, obviously, whenever you stop some particular Java line, okay, you will be able to see the stack frames over there in the debug window. So there you can see, okay, from where the flow reaches to that particular point, okay, you can see so many stack frames, okay. So those are all the stack frames, right? So this is specific to thread, okay. So this first one is specific to thread 1, and second one is specific to thread 2, or something like that. Now these stack frames for thread 1, okay, may not aware of what's happening about the stack frames within the thread 2, okay. So all are independent, right? So this is about stack area, okay. So now now PC registers in the sense program counter registers, okay. So basically this is also per thread, okay. Now here just now we discussed thread 1 is trying to execute M1, M2, M3 methods, right? So each I mean, we have three stack frames for three methods, right? So now okay, specific to thread 1, it will try to note down, okay, the current executing instruction, okay, number. And it will try to note down somewhere, okay, I have executed so and so line number, okay, now I am supposed to execute the next line, okay. So this is also per thread, okay. So this is about the PC registers. Now coming to the native method stack in the sense, sometimes, okay, so within the stack area, just now we discussed about what you say stack frames per thread. So like in case your thread is trying to execute some method, okay, within that method, okay, it is trying to refer some native methods, okay, native methods in the sense which are written in other programming languages other than Java, like C or C++. Okay, so if you try to such kind of methods, okay, then the stack frame will not be formed over here within the stack area. So for that we have one more separate stack memory that is known as native method stack, right? So if you are trying to invoke the methods which are written in Java, then only it will try to form stack frames on top of the existing stack frame. So stack I mean stack area will follow a last in first out strategy. So that's why, I mean, whenever you, I mean, the what you say recently executed method finishes, obviously that respective top stack frame will be removed, okay. So this is about a runtime data area. So here I want to add a few more key points, okay. So the key point number one is till JDK6, okay. What you say method area is handled separately, okay. So this is not part of heap, okay. So method area is also known as PermGen, okay. So and one more point here is string constant pools. So whenever you create any string object, let's say string s is equal to abc, so that literal will be created in the string constant pool, right? Even that string constant pool is also part of method area or PermGen till JDK6, okay. So in JDK 7, okay, so they just moved this method area to this heap area, okay. So I mean, what you say? So within the method area only. So somewhere within the method area, they just accommodated this method area form gen within the heap space in JDK 7 version, right? So um, in JDK 8 version, okay, even they just what you say remove this perm gen from the heap space. So they have started giving a separate memory area known as the meta space. Okay, so meta space is nothing but the same thing. Whatever method area consists of class information data, right? I mean, whatever I said, static variables, class names, parent class names, constructors, blah blah blah. All those things information will be available in metaspace from JDK onwards. Okay, so I mean, so for example, whenever JVM tries to create a new object with some new operator, but okay, so but I mean, by the time itself, let's assume heap area is already full. Heap area does not have a sufficient memory to create your new object. Okay, so then it will try to throw a famous exception Java.lang out of memory error. Okay, uh, so similarly, in the PermGen also, okay, if you are trying to load so many classes, so then obviously you will try to accommodate class information metadata within this method area PermGen, right? So here also there is a possibility to throw java.lang out of memory error space PermGen space or something like that. So obviously, then we will try to increase this PermGen space up to some optimistic threshold limit. Okay, something like 256 MB. So here also heap area whenever we get out of memory area, so as a first step, we can even try to increase this heap space. Of course, we are having few what is the parameters how to increase. So that we will discuss later. Okay, so so now, in JDK8, so just now I said, they have introduced metaspace. So why they have introduced in the sense, just to avoid this java.lang out of memory error for PermGen. So now the beauty of metaspace is, okay. So now metaspace will make use of native memory. Okay, so native memory in the sense, right? Obviously you have enough memory for your operating system, right? So that will try to make use of what you say metaspace from JDK8 onwards to avoid the java.lang out of memory error PermGen. So there is no PermGen concept from JDK8 onwards. So, and one more key point about this runtime data area is, so you might have heard about the famous one more error, stack overflow error, right? So whenever you try to execute some recursion related programs, okay, so then the flow will try to continuously run the same method again and again. So then what you say, it will try to form the stack frames, again stack frame, again it will try to execute the same method repeatedly. Like that it will reach some point where it cannot accommodate the stack frames. So then at that point it will throw a stack overflow error. Okay, so these are the key points about runtime data area. So now we will move to the third component, that is execution engine. So engine in the sense, okay, so so yeah, we have now what you say dot class file which is having a bytecode instructions. Okay, now what you say till now we have discussed. All the memory areas are allocated as per the expectation. So such as Java bits are assigned. Allocated within the heap area. Class level information is allocated within the method area, or local variables or whatever are allocated within the stack frames. So till now, so far, so good. So now, so now, execution engine, what happens? Will try to interpret your dot class file bytecode instructions, okay, to machine understandable instructions. Okay, that is known as native code or machine code. Okay, so why? Because um, your host operating system will try to execute your code, right? So that cannot understand your bytecode. So that understands only machine understandable instructions. That is native code. So that's why here execution engine's responsibility is to convert your bytecode instructions to machine understandable instructions. So in order to achieve that particular task, interpreter will come into picture. What interpreter will do? Interpreter will try to convert each line of your bytecode to each line of your native code, right? So then it will try to interpret very quickly, but sometimes what happens, your code may what to say, may try to execute some other methods which are what to say repeated multiple times. Okay, so at some point you are trying to invoke method M1, okay, and again at line number 15 again you are trying to invoke the same method M1. Okay, then what happens? This interpreter will try to interpret the same method M1 at line number 10 and at line number 15. So two times unnecessarily it is trying to interpret the same method again and again. So just to avoid what you say the execution time, I mean, just to fasten that execution time, this second one came in picture, that is JIT compiler, that is just-in-time compiler. So just-in-time compiler, what it does, it will try to identify those repeated methods, okay, and it will try to what you say, convert those repeated methods, specific bytecode instructions into the native method, okay, sorry, native code or machine understandable code, okay, and then and it will just hand it over that the converted native code to this interpreter, right? So then when interpreter tries to what you say, interpret that repeated method, okay, so then I mean, it no need to interpret once again, it will happily what you say uh, what you say, execute that native code prepared by this JIT compiler, right? So here till now what we have done, we are just trying to convert the bytecode instructions into the native code only till now. I mean, we have just done till that point only. I mean to say, we haven't started the execution of this machine understandable instructions by the host operating system, so that is not yet done, okay. So now the third component is garbage collector. So garbage collector, I mean, in the previous languages C or C++, I mean, it's a programmer's responsibility to assign a memory or to allocate a memory, and for the allocation or deallocation, programmer has to take care. But whereas in the case of Java, now I mean, they have introduced the one daemon thread which runs in the background. Okay, so the purpose of this Java, what you say, garbage collection is, it will try to identify some unused objects or unreachable objects or unreferenced objects. Okay, so and it will try to mark and sweep those objects, so that I mean, it will what you say, it will try to release the memory, or it will what you say, it will continuously it will identify, and it will try to identify those objects, and it will kill those objects, so that by that way it will release the memory, right? So that's the purpose of garbage collection, right? So so with the help of garbage collection, I mean, so just sometime before I said, so within the heap space, I mean, like, I mean, there might be a possibility to have java.lang out of memory error heap space, java.lang out of memory error congen space, right? So now garbage collection will try its level best to what you say, identify these unused objects, and it will try to release the memory. By that way, it will try to try to avoid the scenario of erasing out of memory error. But still, sometimes, I mean, we may get out of memory error, so that's a I mean, that's a different topic. So I mean, we need to optimize the code like in such a way that it should be eligible for garbage collection as soon as we are done with our task. So that we will discuss later. So this is the purpose of garbage collection. So now the final part is this native method interface, native method libraries. What does it mean? So as I said, I mean, your host operating system will try to what you say, execute this machine understandable instructions, right? So now here till now your interpreter or JIT compiler are happily converted your bytecode instructions to what you say, machine understandable instructions or native code, right? So now it's a time to execute those machine understandable instructions by your host operating system. So now how you will interact with your host operating system, in the sense, here you see, with the help of this native method libraries. So native method libraries, in the sense, for example, if you are having Windows operating system, internally you might have seen .dll files in your I mean, what do you say, in the bin directory, okay, JRE bin or JDK bin, okay. So if you are having Unix operating system, you might have seen .so files, okay. So I mean, what you say, how you will interact with your native method libraries with the help of native method interfaces. So now, what you say, your machine understandable instructions are getting executed by your host operating system via this native method interfaces, and native method interfaces will try to interact with native method libraries, and native method libraries will be in touch with your host operating system. By that way, finally, all your machine understandable instructions will get executed, and you will see your output. Okay. So this is the high level demonstration about the JVM architecture. Okay, so I hope I mean, it is clear for you guys. I mean, so if you have any questions, I mean, you can ask your questions in the comments box. Okay, so yeah, so if you really like my video, okay, please like it and share it and subscribe to my channel. Thank you.